Hello, I'm Mr. Craig, and I wish to work out the even problems on this worksheet. Lewis dot structures, worksheet number 1. Let's read the instructions. From the chemical formula on the left, construct the Lewis dot structure for the compound. Next, determine whether the molecule or compound has ionic, polar covalent, or non-polar covalent bonding between the atoms within the molecule or compound. After you finish drawing the Lewis dot structure, assign the correct partial charge. And again, remember our lowercase delta positive and lowercase delta negative for our partial positive, partial negative, or the full charge for each element if applicable. Also, be sure to include how many valence electrons are represented in the structure from each element. So let's start off with the first one. Again, I will work out the even answers here, or questions. So let's go ahead and get those. So just like what we did earlier, let's first of all figure out what type of bonds we have between the atoms. So oxygen, gas, or O2. So we have an oxygen and an oxygen. And the first thing that we want to do is look at the difference in the electronegativities. So go to your notes from the previous time, or the previous packet, and you will again have this at your disposal for figuring out the differences in the electronegativities. So take a look at the difference in electronegativity, and unfortunately we have the same element, which is 3.5. Now, some of you may say, well, wait a minute, do I even need to show that calculation? Absolutely. Be sure to show that. So what that means is we have a difference in electronegativities of 3.5, which gives us a value of 0. So what this means is the type of bond that we have between the oxygens happens to be non-polar covalent. Okay? That's the first thing that we need to do. The next thing we need to do is determine how many valence electrons is represented in this compound from each element. So since we have 2 oxygen atoms, slide that over, each oxygen has, well, let's double check and see. If we look at oxygen, how many valence electrons does it have? 6. Very good. So always have your periodic table out when doing this as well. So we go to our periodic table, find out we have 6 valence electrons. So I have 6 valence electrons, but since I have 2 oxygens, I'm going to multiply that by 2, which means that I have a total of 12 valence electrons represented in this compound. Now, be sure that when we draw out our Lewis structure, okay, remember what I said about making sure that the external atom has its 8 electrons, and then whatever's left over, dump on the central atom. Well, in this case here, we do not have a central atom. So pick one of these to be a central atom. So I'm going to go ahead and say that this is my central, this is my external, and it doesn't really matter what you do. So I'm going to go ahead and assign each of these with a pair of electrons around there. So I'm going to give it 8. Okay. So right now I have a total of 8 electrons represented. Whatever's left, I'm going to put on the other atom. But what I will not do is put them between here, because whether it's on accident or on purpose, if I put electrons between atoms, they are sharing those. So I'm going to go ahead and put the other 4, which represents a total of 12 electrons, that looks like this. So right now I have 2, 4, 6, 8, 10, 12 electrons. The next thing I need to ask myself is, everybody happy? In other words, does everybody have 8 electrons? Well, this atom has 8 electrons. This atom has how many electrons? Very good, 6. 2, 4, 6. So whether, again, if it's on purpose or on accident, if you have electrons between atoms, they are sharing those. So what I need to do is I actually need to move a pair of electrons between these 2 atoms so that now we're going to be sharing. Easy way to remember this, the 1 with 8 is the one you want to manipulate. So, and it doesn't matter where you take the pair from. I'm just going to go ahead, oh shoot, can't move it on this one. So I'm going to take the pair from here and put them in between there. So what I've done is, I've actually taken the electrons that were over here in this quadrant, which again, doesn't matter where you take them from, and I'm moving them between. So now if I look at this, if I draw circles around here, there's 8 electrons, and there are 8 electrons. So what we've created in our first example is a double bond between the 2 oxygens. Now, we don't care about what a double bond means and what a single bond means or what a triple bond means. And again, remember, there's no such thing as a quadruple bond or 4 bonds between 2 atoms. That doesn't exist for what we're doing. So when we look at this, this is oxygen that has 8 electrons. And when you draw circles, again, the circles mean sharing. What kind of sharing? Well, in this case, it's equal sharing when we have nonpolar covalent. So here's what I want from each of these. I want you to first of all tell me what type of bonding we have, draw the correct Lewis structure. Oh, charges. Are there any charges on this? Since it's a nonpolar covalent bond, that means that they're sharing these electrons between here evenly. So there are no partial charges. The only time that we're going to have partial charges is if you have polar covalent or if it's ionic, which we'll have some examples here shortly. Okay, so again, this is what I want. Difference in the electronegativities, the value. I want the electronegative values. I want you to tell me what type of bond is between the atoms, total number of valence electrons, the correct Lewis structure. If circles are applicable there, go ahead and show that. All right, so let's look at number 4. NH3 or ammonia. Okay, so same thing. Now, notice that we have a nitrogen and 3 hydrogens. For what I'm doing right now, whichever one of these is least represented, or only one of, that's going to be our central atom. So we're only going to worry about between the nitrogen and a hydrogen, because when we draw this out, you'll see here shortly that the nitrogen has hydrogens around it. So when we do the difference in the electronegativities, we're only looking at between a nitrogen and a hydrogen, just like what we did on a previous worksheet. So again, go and find these electronegative values. Whoops, we want this one. So nitrogen has a value of 3.0, hydrogen 2.1. So we want to make sure we assign that value. So we have 2.1, 3.5, and again, if you take the difference and it's negative, just drop the negative. So in this case here, we have a difference of 1.4. So what type of bonding do we have between the nitrogen and hydrogen? Polar covalent. Very good. So we have sharing, but we have unequal sharing. Okay. Next thing we want to do is find out how many total valence electrons we have. So since we have NH3, okay, so that means I have, well, let's look at our periodic table. How many valence electrons does nitrogen bring? 5. Very good. How many valence electrons does each hydrogen bring? Whoops. Very good. Oh, whoop, come on over here. We have 1. So since we have 3 hydrogens, each one of those is going to bring 1. The nitrogen brings 5. So in this case here, let's not do that. Let's say that the nitrogen brings 5 electrons, plus we have 3 electrons from each hydrogen. And again, we have 3 of those, 1 of those. So that gives us a total of 8 electrons that we're working with. So we're going to draw our Lewis structure. So put nitrogen in the middle, hydrogen here, and hydrogen here. And again, if you put your hydrogens, one there, left one of the other quadrants empty, we're just fine with that. So let's go ahead and assign electrons. Make sure that we satisfy the external atoms first. And in this case, hydrogen only wants 2 electrons. Recall that since we're in group 1A, it can only have 2 electrons because there's only a 1s orbital. So hydrogen does not get 8 electrons. With that in mind, hydrogen can never be a centrally located atom. Hydrogen will never be in the middle or between other atoms. That can never happen. So we'll give our electrons to our hydrogens. Okay. So right now we have a total of, we have our external atoms satisfied. How many total electrons do we have represented? We have 6. How many do we need? We need 8. So whatever's left over, we dump on the central atom, which looks very nice right there. So when we look at this and we draw our circles, say, okay, well, hydrogen has its 2, each of those hydrogens, and then when we look at nitrogen, there we have that. All right, since we have polar covalent bonding, we do have some charge associated with this. Whichever of these 2 values or elements has a higher electronegative value, that one is negative. Since we're sharing, these are partial charges. So since the nitrogen has a value of 3.5, it will have a partial negative charge. Okay, so that's partial negative, and you can just represent it on one of the hydrogens. Doesn't matter which hydrogen. So the hydrogen has a partial positive charge, the nitrogen has a partial negative charge. Why is that? Because the electrons that are being shared between nitrogen and hydrogen are closer to the nitrogen than they are the hydrogen. Okay. All right, let's look at number 6. SiCl4. Actually, what was the one before that? Yeah. Okay. SiCl4. So again, we want to do the difference in the electronegativity. So silicon and chlorine. So again, even though there's 4 there, just do it between 1. So go to your values. Silicon has a value of 1.8, chlorine 3.0. I think it was chlorine, wasn't it? Yeah. So 1.8 and 3.0. So 1.8 and 3.0. That would give a negative, but just drop it. So it's 1.2. So the value between, or the difference in electronegativity of 1.2 gives us a polar covalent bond. So that means that the electrons that are being shared between the atoms are not being shared equally. All right, so let's find out how many total electrons we have. So silicon, which is over here. Actually, let's get them over here. Silicon is group 4A, so each silicon brings 4. Each chlorine brings 7. Okay, so silicon brings 4. So silicon, 4 electrons, and we have, I believe, 4 chlorines. We do. So we're going to have 4 chlorines, and that's 7. So we have 28 plus 4, which is 32 total electrons. So we've got quite a few electrons that we're going to work with here. Again, arrange your elements. So silicon goes in the middle. Put our chlorines around the horn here. Again, give your external atoms what they want. In this case, chlorine wants 8. Everybody else wants 8 except for hydrogen, which only wants 2. So we'll give, there's 8. Okay, so all the chlorines have 8 electrons. How many electrons do we have represented right now? 8 times 4 is 32. We have all of our electrons represented. So if the chlorines have 8 electrons, does the silicon have 8 electrons yet? Yes, it does. Remember, again, if it's on accident or on purpose, if they're between the element, they are being shared. So the silicon does have its 8 electrons right there. Chlorine has 8. So our Lewis structure looks very, very good. Okay. Now let's assign the partial charges, since we are looking at a polar covalent compound here. Whichever of these has the higher electronegative value is more negative. So in this case, chlorine 3.0, silicon 1.8. So in this case, chlorine is partial negative, and the silicon is partial positive. Okay? Isn't that fun? All right, let's look at number 8, carbon monoxide. And I might need to erase that since we're going to need some space here. Okay. All right, carbon monoxide. The first thing that we have to do is actually write out this formula. So carbon monoxide, so carbon, and again, that tells you that you have a nonmetal with a nonmetal. So we don't have any Greek prefix in front of the carbon. It means you just have a C. Monoxide, we only have 1 oxygen. Okay, so that's our formula. And yes, you are still responsible for being able to write that. So let's do the same thing that we did up above. Let's find the differences in the electronegativities. So if I have my C and my O, and I only have 1 of each, find out the value. So carbon 2.5, oxygen 3.5. Not too bad. So 2.5 and 3.5. So the difference between that, yes, I know it's negative, drop to negative, 1.0, which means that we have polar covalent bonding. Notice that a lot of these are polar covalent, which is fine. All right, so let's go ahead and get our electron count. So we have 1 carbon and 1 oxygen. So carbon brings 4, oxygen brings 6. Okay? And yes, I know you can do that math in your head. Please still show that. So carbon brings 4 electrons, oxygen brings 6, which means that we have 10 electrons total in our compound. Carbon and oxygen. Now, as a heads up, anytime you see carbon, associate that as a central atom. Just go ahead and do it. It'll save you a lot of heartache and pain, because when we see carbon, carbon is always centrally located. Hydrogen is never centrally located. Easy thing to remember, especially when you get into organic. So since we are saying that that's central and that's external, easy to do. Give the external, it's 8 electrons. So right now we have a total of 8 electrons shown. We need a total of 10. Do not put the last 2 right here. You can put it in any other quadrant you want. I'm going to actually put them down here, but it doesn't matter where you put it. So some of you are like, ooh, I don't like it down there. Okay, then put them right there. That's fine. Doesn't matter. So when we look at this, we have to ask ourselves, does everybody have what they want? In this case, does everybody have 8 electrons? Oxygen has 8. Carbon has, very good, 4, remember. We have these 2 electrons here. So what we need to do is we need to start swinging some pairs until everybody has 8. And again, I don't want to say this very often, but the one with 8 is the one you want to manipulate. So, and it doesn't matter from where you take them, just don't take them away from here and then put them back in there. So I'm going to take these 2, whoops, take those 2 from the bottom, and I'm going to swing them around, put them right there. So right now, does oxygen still have 8 electrons? Yes. How many electrons does carbon now have? Very good, 6. So what we want to do is we want to take another pair. Actually, I'm going to scoot the carbon over. And I'm going to take a pair from somewhere, doesn't matter where. You want to take them from the top, that's cool. And put them right there. So what we just created is a triple bond. Notice how oxygen still has its 8 electrons, right there. And this carbon also has 8 electrons. So any time that we put electrons between the atoms, whether it's on accident or purpose, they are sharing. All right, so we have our correct Lewis structure. What we need to do is assign partial charges, since we do have a polar covalent bond between. And again, don't freak out and go, ooh, is that one 3 times strong? We're not worrying about that right now. So oxygen has a higher electronegative value, therefore it is partial negative, where the carbon is partial positive. Okay? All right, number 10. Here we have our first bracket. Awesome. Okay, NO, and it's a polyatomic, which you don't need to know yet. NO with a -1 charge. Again, remember what that -1 means. That means that we have a different number of electrons from that which the atoms brought. If it's negative, that means we have additional electrons. If it's a positive charge, which was earlier on in the homework, that means that structure is losing electrons, because it, again, negative charge means that we're gaining more negatively charged electrons. So the first thing we want to do is find out what type of bond we have between the nitrogen and the oxygen. So nitrogen and oxygen. So we go back to our table and look. So nitrogen has a value of 3.0, oxygen 3.5. Okay, keep that number in your head. So nitrogen 3.0, oxygen 3.5. Difference of those 2 values is 0.5. So shocking, we have a polar covalent bond between the nitrogen and the oxygen. Next thing we want to do is find out how many total electrons this is bringing along. So nitrogen has 5, oxygen has 6. Okay. Did I do those values right? Yeah, those values are right. So we have 5 electrons plus 6 electrons. But since there is a -1 charge, that means that we're also adding 1 more electron. Now, the good news is we don't care where that electron's coming from. And we don't need to designate where that electron's at within the compound. We just don't care. If you're sharing with somebody, then you don't say, that's mine. We're sharing my thing. If we're sharing, and it's ours. So all we care about is how many available electrons we have, and then we're going to distribute them so that everybody's sharing the way they should. Okay? So when we add all these up, we get a total of 12 electrons. Okay, so we have to keep that in mind. So we have 12 electrons, if I did my math right. Yeah, got 12. And again, we have nitrogen and oxygen. Doesn't matter this time who's a central atom. So I'm just going to say oxygen's outside because it's on the right side. Doesn't mean anything. So I'm going to go ahead and put 2 there, 2 there, 2 there, 2 there. So in this case, my oxygen's happy. And I have 8 represented, but I need a total of 12. So let's put 4 more just somewhere. And if you want to put those on top and leave the bottom empty, that's fine. But ask yourself this, does everybody have 8 electrons? The oxygen does, but the nitrogen only has 6. Very good. Don't forget, they're in between. So that means that we need to take a pair from somewhere, and just to keep it symmetrical, I know how some of you are, take that pair there and move it in between, and now everybody has 8 electrons, which is nice. Now, here's one thing that I don't want you doing, because you might have a friend in a different chemistry class and it's like, oh my gosh, you have to tell me which one of those electrons didn't come with the nitrogen or the oxygen. No, we don't. We don't care. However, what we do need to do, since we have an extra electron from somewhere, we have to use what's called brackets. And again, the brackets tell us 2 things. The first thing, we have a different number of electrons from that which we started. We originally started with 11, but somebody donated their electron to this compound so that it could have an even number. That's what we're looking for. So the first thing that the brackets tells us is that we have a different number of electrons from the value or the original number of valence electrons that we started with. The second thing it does is tells us how many electrons were donated or given away. How do you do that? You show a charge. So the -1 means that somebody gave this compound 1 electron. Why? Because the overall charge is now a -1 charge because of that additional negatively charged electron. So when we look at this, this is our correct Lewis structure. But are we finished yet? Not yet. Hang on there. So we have to give our partial charges. And since nitrogen's 3.0, oxygen's 3.5, the one with the higher electronegative value is more negative. So the oxygen is partial negative. I'm sorry, the oxygen's partial negative and the nitrogen's partial positive. So there's our complete Lewis dot structure. Okay, isn't that fun? On number 11, when you're drawing this out, make sure that you evenly distribute the carbons. So if you're doing it like this, so you had 2 carbons, put the carbons in the middle, put an oxygen there, oxygen here, and an oxygen here. And then satisfy the external atoms first. And again, you got a lot of work to do before that. Whatever's left, dump on this central atom, plural. Make sure everybody has 8. You might have to move a few electrons around, circle them up, do partial charges, brackets. Okay, so this one's a fun one. Okay, and I'll leave that one up to you because it is so fun. All right, number 12, CH3. Okay, here we have a multiple carbon situation. So again, what we're looking for first off is the difference in the electronegativities. So between a carbon and a hydrogen, and I'm not going to worry about the differences between the carbons and carbons. When we get in AP Chem, we'll talk about that. But what I'm primarily looking for is the central atom and the external atom relationship, and that's what we're going to focus on today. So when we look at carbon 2.5, hydrogen 2.1, so our differences, so 2.5 and 2.1 gives us a value 0.4, so that means that we do have a polar covalent bond situation there. Wow, okay. So we do need to find out how many total electrons we have. So we have 3 carbons and 8 hydrogens. So we have 3 times, how many electrons does carbon have? Very good, 4. And again, hydrogen has 1 electron. Okay, so we have 3 times 4 electrons, that represents our carbons. And then we have 8 electrons, 8 hydrogens with 1 electron each. And when we add those up, so we got 8 plus 12, which is 20. So that's how many total electrons we must represent in our structure. All right, so since we have C3H8, let's go ahead and put the carbons in the middle like they belong. And then put the hydrogens around. But again, keep in mind about the quadrants. So we'll put hydrogen there, so there's 2 quadrants. And there's a quadrant with the carbon already in that quadrant. And we got to go below there. Okay, so now we have carbon in those 2 quadrants. Here we have 2 more. There's one, that's a total of 7 so far. And there is 8 hydrogens represented. Notice, no hydrogens are between the carbons. Can't do that. Also, when we have neighboring atoms, if they have electrons, say, for example, that these were not hydrogen, and say they were something else, and we had electrons next to them, these atoms don't share, it's only this way. And we'll talk about that a little bit later on, especially when we start doing some more interesting Lewis dot structures. And we start to build some models. So the electrons, the atoms that have electrons here, they're not sharing. They're only sharing where you see the sticks. So that'll make more sense once we draw and actually construct these things. All right, so let's satisfy the external atoms first. Again, we're looking for a total of 20 electrons. Hydrogen only wants 2 electrons each. So satisfy and give them their 2. So let's clean that baby up. Okay, so now we have 2, 4, 6, 8, 10, 12, 14, 16 electrons represented. We need 4 more. And if we look at it, these carbons have, or this carbon has 6, this carbon has 6, this carbon has 4. So if I go ahead and place whatever's remaining between these carbons, I added 4 because I had 16 originally. Now I have 20. This carbon has 8. This carbon has 8. That carbon has 8. And all the hydrogens have 2. So when you look at it and draw your circles, everybody is happy. Okay, yeah, there. Okay, now that looks very confusing. Okay, but again, on paper, your lines won't be as thick as mine, but that's fine. So we got, everybody's happy. The hydrogens have 2. Each carbon has 8. Okay, so the last thing we want to do is the differences in the electronegativities. So you don't have to show it for each element, but we want to find out who has a higher value. In this case, carbon has a higher value, so it gets the partial negative charge. And the hydrogen gets the partial positive. Okay. Pretty nice. So again, carbon always is centrally located. Hydrogen never is centrally located. Okay, let's look at, let's go ahead and do potassium nitride. Okay, and we'll skip this one. I'll let you do 14 on your own here. So let me zap this. I can't remember if we do an ionic one. And if we do, then great. We'll have more practice. Okay. All right, so here's number 13, potassium nitride. Now, when writing this out, make sure that you're actually writing out what this is. And this is what we did before fall break. Remember potassium? Where's potassium? Over here. So potassium is a metal. Okay? So don't forget where potassium is located at. And let's get that back over here. So potassium nitride, so we have a potassium atom. So we're going to write out the formula. And probably not a bad idea to write the charge. Potassium has a +1 charge. Why? It's over there. Nitride is nitrogen. So we have nitrogen. And what's the charge on nitrogen? When it's with a metal, remember, we don't have it written up here, but -1, -2, -3. So all the nonmetals here, -3, all the nonmetals here, -2, all the nonmetals here, -1. So our potassium has a -3 charge. Are the charges balanced? You're like, holy cow, I can't believe we have to do that again. Yeah, you get to do it all year long. So make sure you don't forget this. So potassium's +1, nitrogen's -3. So that means that we need 3 nitrogens. I'm sorry, potassiums. So in this case here, that's our chemical formula. We need to do this first if you're not given a molecular compound, which has the Greek prefixes, which we did the other day. So here's our ionic compound. And as we just demonstrated, we have full-blown charges because you have a metal with a non-metal. But to validate that, make sure we do the differences and the electronegativities. So that means between a potassium and a nitrogen. What kind of bond do we have between there? Well, we got to find out. So potassium has a value of 0.8. Nitrogen has a value of 3.0. So when we do that, we have a 0.8 and a value of 3.0. Take the difference of those two. Yeah, we get a negative, drop it. So it's a value of 2.2. So if your electronegative difference is 2.2, you definitely have an ionic compound. Which means that these elements are not sharing electrons. Ionic is not sharing. Why? Potassium has an electron, which we'll talk about here shortly, and it donates it, gives it away. That's why it has a +1 charge. All right, so let's find out how many valence electrons we actually have in this. We still have valence electrons. So based on our equation, and you have to do this first before you can determine valence. So we have 3 potassiums and 1 nitrogen. So when we look at that, we have potassium. How many valence electrons does potassium bring? Very good, 1, but we have 3 potassiums. So that means that we have 3 potassiums plus how many nitrogens are in this compound? That's right, only 1. And how many valence electrons does nitrogen have? 5. Very good. Has a -3 charge, but it has 5 valence electrons. So I'm doing this. 5 electrons. So add them all up. So it gives us 8 valence electrons. Okay. All right. Now something unique about the ionic compound. What we don't do is we do not show circles. Why? We're not sharing electrons. So when we draw Lewis structures for ionic compounds, you have a choice. You can show it with its 1 electron, but do realize since it has a +1 charge, it's giving that electron away. And let's do it like this. Let's go ahead and put our nitrogen here, and our potassium here, and our other potassium here. So I'm going to go ahead and do this. I'm going to give them what they started with. Okay. So in that case, it looks like that. And nitrogen started with 5. Okay. And actually, I'm going to change the color there. Not that you have to. I'm just going to. Let's go with black. Okay. And again, it doesn't matter. So what are each of those potassiums doing? That's right. They're giving their electron away to the nitrogen. So that electron goes from here to over here, somewhere on nitrogen. So it goes from there to there. That one goes over to here. This electron goes over to there. So what has happened is nitrogen is now happy because it has 8 electrons, where potassium no longer has any valence electrons. And it's happy. That's what potassium wants to do. However, we must represent this correctly by drawing a bracket around it. What does a bracket represent? 2 things. Has a different number of electrons from that which it started. It originally had 1 electron, it gave it away. How many did it give away? 1. So we write a +1 charge on there. Same thing with this nitrogen. Started with 1, gave 1 away. Same thing with this potassium. Started with 1 electron, gave it away. The nitrogen started with 5 electrons, but these 3 potassiums gave it the 3 electrons. So it has a -3 charge. We're done. We have our structures so that the elements are represented with the correct number of electrons. There are no valence electrons for our metals. That's what metals want to do. They want to give them away. That's why they have positive charges. And our nonmetal is represented with the 8 electrons. How many? 3. That was given to it in addition to its 5 valence electrons that it started with. So, as a heads up, your nonmetals will always have 8. Your metals will always have 0. But we have to do this first before we can do that. Because it gets really complicated if you just start with 1 potassium and 1 nitrogen and say, well, there was only 1 and they had 5, it only has 6. Something's not right. Exactly. What that means is that we need more potassiums to donate more electrons for the nitrogen to be happy, or for everybody to be happy. Okay? So that's ionic. And how do you know it's ionic? You do the difference in electronegativities. You recognize that there's a metal with a nonmetal. Those are big, big indicators for you. Alright, so I'll let you do the potassium on your own, or I'm sorry, the phosphate on your own. Let's look at number 16. Okay. We have CH2Cl2. Interesting mix there. However, here's what we do have. We have carbon that's in this compound, which means that that is our centrally located atom. Which means that carbon is bound to a hydrogen and a chlorine. So that means that we have 2 differences in the electronegativities. So, let's do it. So we have a carbon with a hydrogen, and we have a carbon with a chlorine. Okay, because we know carbon's going to be in the middle. You see something like this, carbon's always going to be in the middle. So let's find out the differences in the electronegativities. Carbon 2.5, hydrogen 2.1. Okay, so carbon 2.5 and hydrogen 2.1. So that gives us a difference of 0.4, which tells us that this type of bond is polar covalent, which is what we would expect. And the chlorine has a value of 3.0, which means that we have another polar covalent bond. Okay. However, what's interesting is, in this scenario, the carbon has a partial negative charge. In this scenario, the carbon has a partial positive charge. And that's okay. I don't want you to freak out about that. That's okay. So, in some cases, that could happen. Okay? But we do have 2 polar covalent bonds. What you will not have in a compound is a polar covalent bond and an ionic. That is not going to happen. I promise. But we could have polar covalent and non-polar covalent. That's okay. We can deal with that. So let's get our number of electrons. So we have 1 carbon, 2 hydrogens, and 2 chlorines. So we know carbon has 4 electrons. We know that hydrogen has 1 electron each. And the chlorine, again, if you look on the periodic table, chlorine's over here. Chlorine has 7 valence electrons. But we have 2 of those. So we're going to go ahead and 2 times 7. So we have a total of 28 plus 2, which is 30, plus 4, which is 34. So we have 34 electrons that we're working with in this compound. Okay, so C, again, goes in the middle. Put the carbon in the middle. So we're going to put it in the middle. And then 2 hydrogens, and it doesn't matter where you put it. And we'll talk about that significance later. I'll just put it here and here. And 2 chlorines, there and there. Again, seriously, it doesn't matter. If you wanted to put the 2 hydrogens here or the 2 hydrogens here, I don't care. It doesn't matter. All right. All right, so we need a total of 34 electrons represented. So let's satisfy the external. There's 2. There's 2 more. Okay, the hydrogens are happy. Chlorines. Okay. So when we look at it, we have 8 plus 8 is 16. Did I do that right? Hold on. I can't count. Let's try that again. 2 times 7 is 14, plus 2 is 16, plus another 4 is 18. Sorry about that. All right, so we have 16, still can't count. 14, it's 20, my goodness. So we need a total of 20 electrons. All right, 14 plus 2 is 16. 16 plus 4 is 20. All right, so we have 16, 18, 20. So we have all the electrons that we're supposed to have on this compound. Does everybody have what they want? Pretty good. So we have 8 electrons there. We have 8 electrons there. Hydrogen only wants 2. And the carbon, looky there, has its 8. So everybody's happy. Now, here's the fun part. When we look at the differences in the electronegativities, okay, again, carbon and hydrogen looks like this. So carbon has a partial negative charge, where the hydrogen has a partial positive. When we're looking at carbon and chlorine, carbon now has a partial positive, where chlorine has a partial negative. What I don't want you to do is get upset by that fact. Because here's what's happening. The electrons that are being shared between the carbon and the hydrogen here, these 2 electrons are drawn a little bit closer to the carbon than the hydrogen. The 2 electrons that are being shared between the carbon and the chlorine, these 2 electrons are being shared a little more closely to the chlorine than the carbon. What I don't want you to do is go, oh, I see. If I have 2 of these that are partial positive, that means that the carbon has a partial value of -2, where over here now it's a partial positive of 2, where the chlorine, no, let's not do that, because we're not going to ever worry about how close those electrons are, and it does change the partial value of that charge. So just to make things simple, just do something like that. And so when you look at it, kind of relate it in this way. Whenever you do your partial charges with multiple things, kind of put them in the same area with a tracer going to it. I know that sounds a little confusing, but that's probably the best that we can say about that. So there's our Lewis structure with the correct partial charges, and it does look fun. All right, so let's look at the next one. Number 18, BF3, boron trifluoride. Okay. Oops. Not sure what happened there. Okay. So BF3, and again, boron and fluorine. Okay. So when we look at these values, whoops, not those. Let's look at these. So boron 2.0, fluorine 4.0. So 2.0, 4.0. Difference of there, 2.0. So that means that we have an ionic bond. Okay. And honestly, this is one of those that doesn't really follow the ionic bond. But if you wrote it up and I gave this to you as a test question, I would give you credit. But this actually is a polar covalent bond. Okay. So this is one of those weird ones. It's like, what? Yeah. So again, this is a general trend. Boron is a moron. And what's even more bizarre about boron is it doesn't like to have 8 electrons. It only wants 6. So I threw this in here just as a curveball, just to show you a few weirdos, which is fine. But so we're going to say, even though the value says it's 2.0, this technically has polar covalent bonding. Okay. If you said it was ionic, that's fine, but I'm not going to give you this type of question on a test. Okay. So since it does have polar covalent bonding, let's go ahead and find out how many electrons it has. Boron brings 3, fluorine brings 7 each. Okay, so let's go ahead and get that. So boron brings 3, and then the fluorine, and there's 3 of those. So 21 plus 3 is 24. And again, boron's the moron. So we'll put boron in the middle, fluorine's over here, and here, and here. Satisfy the external atoms. Okay. Now, everybody's happy. And I know that we don't have an octet here, but boron, based on where it's located on the periodic table, that's all at once. Okay? And technically, boron is not a true non-metal. These things here actually act as metalloids, so they kind of have metallic properties and non-metallic properties. But again, that's well beyond the scope of this class. So the reason why I'm giving you this example is because in AP Chemistry, we deal with boron trifluoride quite a bit. And that's what we call it, boron trifluoride. So when we look at this structure, boron's happy with 6. So boron and hydrogen are the 2 exceptions to the octet rule. And when we draw it, it looks like that. Fluorine obviously will always be more negative than anything else it deals with. And boron's partial positive, looks like that. And that is that, unfortunately. All right, I am going to do number 19 because carbon dioxide I'm sure you can do on your own. So I'm going to do the sodium chloride because, again, it's a little bit more interesting than the carbon dioxide. So let's do that. Chloride. And just like what we had earlier, we have chlorine right there, and sodium is right here. Group 1A, that's a metal, very good. So what that means is we have to write out this compound and balance charges. So don't forget to do that. If you got a thing that's over in group 1A, 2A, or a metal in 3A, then generally speaking it'll be from groups 1 and 2. I'm not going to make it extremely difficult. So we've got sodium, group 1A, which brings 1 valence electron, which means it has a +1 charge. So sodium's a +1, chlorine is over here, which has a -1 charge. So sodium chloride is written and balanced as written. Okay, so that looks good. Now let's go ahead and get our differences in electronegativities. So sodium has a value of 0.9, chlorine 3.0. And you should be thinking, yeah, this is going to be a ionic compound because we have full-blown charges here. So sodium 0.9, chlorine 3.0, which is a difference of 2.1. Now, the difference between this and the boron trifluoride, which had a value of 2.0, the close proximity. The farther those elements get away from each other, the more ionic the character is. That's why the boron trifluoride, since they're essentially neighbors, that's why I kept that as polar covalent. That's a bigger concept that we'll deal with in AP Chem. All right, so since it is 2.1 and we have a metal in this, then that means that we have an ionic compound or an ionic bond between them. So let's find out how many electrons we bring. So again, sodium brings 1 electron, chlorine, which is over here, brings 7 electrons. So we have a total of 8 electrons. Okay. Again, sodium, if you want to represent it with its 1 electron, that's fine. And chlorine, with its 7 electrons, since we know this is ionic, that's fine. Okay. Realize that electron is going over here. Okay. Boom. And I'm going to change its color to red just to represent that. Don't have to change color, but I just want to show that that electron that I have personally drawn on this is from the sodium. You never have to do that. Since the sodium started with 1 electron, or 1 valence electron, and it no longer has the valence electron, we put brackets around the element and tell everybody how many it lost. Lost 1. That's why that's a +1 charge. The chlorine had 7 electrons. The The sodium gave it 1, so it now has a -1 charge. So this represents our ionic compound Lewis dot structure. All right, we did quite a few examples here, not necessarily all the evens, but I hope this was beneficial.